All right, so this chapter is pretty short. It's pretty much just all about like physical versus chemical properties and changes. We already kind of covered physical versus chemical uh, properties in the very first chapter, but we're going to get a little bit more into them here, and then we'll add in the changes. So, uh, a physical property is a property of a substance that we can show or measure or observe without it interacting with another substance. So, things like color, luster, which is like how shiny something is, malleability, how well we can bend things. Melting point, boiling point, the density. So melting and boiling point, it is true that that substance is going to have to change a phase, maybe from a solid to a liquid or a liquid to a gas. That is fine. Water is still water, no matter if it's in the ice form, the liquid form, or in the steam form. So it's still just water as long as it's not interacting with something else. That would be its physical property. And density is just, again, that measure of how much mass is in a volume. So density of substances is different at every single different temperature, but we can measure that without it interacting with something else. Now, a chemical property is a property that will show how it interacts or transforms with other substances. So things like flammability, corrosiveness, reactivity, how reactive it is, really is the chemical property. So if we think about copper, for example, we've got physical properties on the left and chemical properties on the right. So copper is malleable, which means it can be formed into sheets or foil, and it can be shaped into wires, which is called ductility. It can be melted and mixed with zinc to form brass. Now, there we're talking about a mixing. They're not actually reacting with one another. We're just mixing zinc to form the brass. There's its density, its melting point, its boiling point. Again, even though it's changing from solid copper into liquid copper, that temperature is just where that happens. It doesn't matter if it's solid copper or liquid copper, it's still just copper. Its chemical properties, it'll slowly form a blue-green carbonate in moist air, the Statue of Liberty. It reacts with nitric or sulfuric acid, and it shows a deep blue color when it's in ammonia. Now, how is that different than physical versus chemical changes? Well, with our properties, that we're really just kind of looking at one substance. A physical versus chemical change, the change, we're really looking at how that substance is like actually changing. So, physical change, what I want you to think with a physical change is I am not changing the substance. Okay, so it would be, for example, any of our phase changes, so melting, boiling, freezing, as long as you are just changing it in that way, where we're not adding any other substance in there and we're just changing what phase it is, that would be a physical change. Things like cutting, grinding, bending, tearing apart, those sorts of things are just physical changes. If we snap a piece of wood in half, it's still just wood. You just have two smaller pieces of wood. So when you are thinking physical change, I want you to think to yourself, okay, is that change still resulting in the same thing afterwards? Um, melting and boiling and freezing, those are all a little bit more difficult to understand just because you do actually see a change happening, but in the end, it's still, for example, just water. A chemical change, however, the particles change and new substances are formed. So you could have things burning or corroding. Cooking is a great example. An egg being fried is a good example. Rusting. So when you see chemical change, or when we think about chemical change, the thing I want you to think about is, can we get our original thing back without reacting it in some way? Physical changes, I mean, yeah, you probably won't be able to get, the two pieces of wood back together, but at least those are the same pieces. However, if you take a look here, if we're taking water in those test tubes and then we're applying some electricity, eventually you're going to get hydrogen gas and oxygen gas. You would have to do a reaction to get those gases to come back together to form water. And so that's why that's a chemical change. So again, to determine whether it's physical or chemical, I want you to use this question. Did the substance's particles actually change? If they didn't actually change, it's a physical change. If they did change, it's a chemical change. So let's go through and practice these. Number one are physical versus chemical properties, and this number two is physical versus chemical changes. All right, so I'm going to do a P for physical and a C for chemical. Acetic acid melts at 16.5 degrees Celsius. Well, that's its melting point, so that's just a physical change. Sodium hydroxide is corrosive. When we talk about corrosive, we're talking about how it interacts with other substances, so that's a chemical change. Gasoline being flammable is also a chemical change. We would have to react gasoline with some oxygen and obviously a spark to get it on fire. And the density of water is 1 gram per milliliter. That is a physical property. So those are all our properties. The next ones are our changes. So letter A, water vapor condenses on a glass on a warm day. This will be a physical change. Remember, condensation is a phase change. You're just taking water as a vapor or a gas and turning it into liquid water. Iron and oxygen react to form rust. That is a chemical change. We've got substances interacting with each other to make a new substance. A piece of paper is burned. Okay. At first, you might think, okay, that's a chemical or a physical change because it's, we're just taking the paper and it's not really doing much. But in the end, that is a physical or a chemical change because we are getting a new product at the end. That ash is really just a bunch of carbon, and we were left with carbon dioxide and water vapor also being produced. A chunk of metal is flattened into foil. This is a physical change. We didn't take that metal and change it in any ways other than just its shape. So that's why it's a physical change. All right. And then the last thing we just want to talk about is energy. Energy is the ability to do work or cause change. Potential energy is stored energy or energy that could be used. And some examples would be gravitational, which is energy due to how high off the ground you are. Elastic is rubber bands, tennis balls, slingshots, that sort of thing. It is energy due to a change in its normal shape. And then chemical energy is also potential energy. Within each bond of a molecule or a compound, there is energy there, and that energy can be released and used. Kinetic energy is energy due to motion. So we have mechanical energy, which is just like our normal motion. If you're measuring the energy of how fast a car is moving, that's mechanical. Thermal energy is the energy due to particles motion, and then electrical would be the motion of electrons. And the reason that we really care about energy is thinking about the fact that energy is conserved, meaning that it cannot be created nor destroyed. It can only be transferred from one type to another. So here is one long example. We've got light energy from the sun. Light energy is kinetic energy. It's energy of motion. So light energy from the sun is converted into chemical energy in plants through the process of photosynthesis. And then that chemical energy is converted into mechanical and thermal energy in animals when we eat those plants. So that is just kind of one long story problem of how energy is changed.